to it later when you need to next week. All right? You guys have a great weekend. Nice long. Well, not a long weekend this weekend anyway. All right. So let's go ahead and do the truss assignment that you guys were tasked with. We'll just talk it through step by step. Again, when you watch those videos, hopefully those are sort of a way to sort of break out all these individual widgets and what they're actually doing. At least that's the idea. But we can do it here as well in person in class. I keep dripping all over my glasses because I had to walk and cross campus and back, and now I'm all sweaty. It's pretty gross. Okay, before I gross anybody else out, I'll just stop talking about it. Open. Let's see. All right. You guys ready to do some trusses? All right, really quickly. When in doubt, architects like to be applied for superpower. What is your very, oh, you don't have, I was gonna say, what's everybody's superpower when you're an architect? Sketching, right? Do you have a dry erase marker?
No, I actually
Oh, yeah, I don't have a marker. Dang, no, I just don't have it. Crud. Oh boy, the day just keeps getting better and better. All right. I mean, they're not expensive. All right. Never mind, I was going to draw something. What are the two ingredients we need to make a truss the way we made one last week? What's that? Did you guys just use a curve this time? Is that it? Okay. The one ingredient then, a curve. All right, we can draw a curve. We can make I'll just make the simplest curve ever, a line. All right. I drew that in Rhino, right? Let's open that Grasshopper interface up. Get to coding right away. All right. Now, really important, going back and forth between Rhino and Grasshopper. First of all, anything you do in Grasshopper, it will preview in Rhino, but really all you're doing is you're moving that graph, and that's what you're designing. When you save in Grasshopper, you're saving that graph, that mind map, right? All the widgets and all the rubber bands connect them up, right? That's it. In fact, if you open it up, and I think it's just like a C# file or a Python file, right? I mean, it's literally just, you open up a text editor, it's a bunch of code. All right. And in fact, when you bring on one of those widgets, you can double click on it and actually see the underlying code for it. All right, so let's see. But what's really handy is when we have something in Rhino that we've been working on, we want to bring it into Grasshopper and start to parametricize it, right? We want to maybe break it up into pieces or use it to build a truss out of, right? In this case. So when we go to the params tab down at the very left here, along the top, perm, I guess, is short for parameters. And you'll see that here at the left, we have geometry, a set of geometry widgets, right? These are all placeholders for us to bring in geometry from Rhino if we want to, right? You see, same as you see the toolbar over here on Rhino, right? We have points, curves, lines, surfaces, meshes. Not a big surprise, we have points, all kinds of different curves, planes, surfaces, meshes, etc. here, right? That we can bring into Grasshopper in order to do something with them. So let's just take a curve, and you can see right away it's orange, meaning that it's empty. It has nothing, no data inside of it. It's not feeding any data to the right. It's not receiving any data from the left. If we wanted to receive data from Rhino, we have to right-click on it and say, in this case, set one curve. And Grasshopper will disappear, showing us the Rhino interface, begging us to select something in Rhino, right, to reference back into Grasshopper. So that's what I'm doing. I'm just go ahead and click this line or curve. There it is. And now, when I highlight this widget, select it, you can see the requisite piece of geometry that it creates is also highlighted in green and Rhino. Yeah, not too bad. Nice one-to-one relationship there. All right, next step, right? Think about the algorithm, the recipe. How do we make a truss out of a curve? Add vanilla extract, 2 eggs. No, what do we do? Yeah.
You need points to divide.
Say it again?
To make a truss out of a curve.
Yeah, let's see. What's the next step here? we have like a bottom chord, right? We need to make a top chord. How do we do that? How is the recipe working that we ran?
Getting another curve,
Yeah, we need another curve. How do we generate that curve?
make another line, and do the same thing you just did with Grasshopper.
Break it down step by step.
Point on curve.
Yeah, let's find a point on that curve. Then we can project up from that point in whichever direction we want. Then we have another vertex that we can draw that top chord, right? That curve. All right, so step by step. Don't take anything for granted. Just like if you were drawing this manually with drafting equipment at your desk, right? We're literally doing it here, just digitally. And we're not moving anything around. It's not tactile, right? We're orchestrating. We're setting the rules and instructions. We can edit it any time. And the computer crunches all the stuff for us, right? Okay, so let's do that. Let's find a point along a curve. A curve or a line, right? It's a one-dimensional piece of geometry when it comes to the topological domain of mathematics. Now that's a very fancy, lots of big words saying that you can move in one direction, back and forth, along a curve or a line, right? Just like with a road. You move to the east, you get a different street address. You move to the west, you get a different street address, right? And they stack up or down, right? Those numbers. Same thing here. Now, in geometry, for a curve, we call that address along the curve a t coordinate, right? So a t parameter. And so if we can say evaluate the curve at a t parameter, right? Then let's take a look at this, right? It says, well, first of all, it wants the curve to evaluate, right? Then it wants the address, the street address, along that street, that curve. So let's plug that in. As I mentioned before, if I go to the params tab, again, I know this isn't completely intuitive at first, but with practice, you start to understand where some of these most used widgets are. Number slider, we can make this a variable. We'll plug that in, and now we can place a point along this curve. Now look what happens. I'm going to zoom way in here. You can see that along the total length of this curve, I'm only going just a small portion of this curve from 0 to 1, right? That's because the curve is bigger than just one unit, right? Like 20-some units. Right? Here's what's interesting about the parametric geometry, right? Like we go behind the curtain, so to say, is we can just tell it to reparameterize that curve, normalize the start and the end of this to go from 0 to 1, right? So if we do that, then suddenly it becomes much easier to sort of understand where the end point is, the start point is, a midpoint, right? In fact, Rhino does this already, CAD does it already for us. A lot of CAD programs do it for us, right? When it comes to snapping to midpoints, snapping to endpoints, etc., right? Basically just looking underneath the hood, looking at that curve and saying, well, where's the address? Halfway along would be 0.5. Quarter of the way along would be 0.25. 3/4 of the way would be 0.75, etc., right? Okay, so anyway, when I do that, then I can start to go along the entire length of the curve. And in fact, I can put this anywhere I want. And what next? We have a point. We're going to project up from it, right? Let's draw that line in the z direction. I did this once, actually more than once, at universities in Canada. And it bugged me to no end that they would correct me and tell me to call it Z instead of Z. Really quickly, I hate this grid. In fact, I hate the light gray that the default screen is in Rhino. I can't think of anything more muddy, mediocre than that gray. I'm going to turn off this grid. It's just visually distracting for me. And hopefully you guys can see a little better, particularly in the recording here. I'm trying to think a couple steps ahead. All right, but we have a point, right? Now we need to give it a direction and length, and we can establish a line off in space somewhere, right? Indeed. In fact, if we go to, again, we think about how we create these things, right? The toolbar over here, points, curves, surfaces, meshes. Not a big surprise. We have things called vectors, which include planes and points, then curves, then surfaces, then meshes. Yeah, it makes sense, right? Okay, so if you know Rhino, you know Grasshopper. It's really kind of nice that way. So we'll do point, line by start point, direction, length. You guys did this already over the weekend, right? Yeah. All right. By default, I think it's already sort of established that the x, or the world plane is xy plane, and that the world z is the z, right? So I think by default this probably already goes in z, right? But you know, if I want to double check that and make sure, I can go to the vector tab. I can find under planes, vectors, sorry. I can give it the z vector, the world z vector here. And of course, length can be something that's variable. So we can, again, give it a number slider. Come on now, there we go, okay. And I can, of course, double click on that label for the number slider and open up its properties. And I can change its minimum, maximum values. So let's do that. Let's make that maximum a little bigger. We can make this thing tall and deep if we want to. All right, and of course we can always change if we want it to be symmetrical or asymmetrical along that t parameter. All right. We have this line, we have the start point, and we have this line, we need to find its end point, right? That's gonna be one of the key ingredients for drawing that top chord, that bow, right? Okay, so not only that, but we need the start and end point for this line, or this curve too, right? So we need this point, and this point, and this point. All right. We have a curve, we want to find points from it, so we go to the curve, analyze, right? I'll drop in a couple of these widgets. So we can find the endpoint for this one, and the endpoint, start point for this one. All right, now it's a matter of just drawing a curve. I'm going to use an interpolated curve. I'm going to hold down the shift button. I'm going to give it this start point, and this endpoint, and this endpoint, and voila. Right? We have a curve that interpolates between those 3 points. Not arc, but a spline. Right. Again, remember, data goes from left to right. So if we want to find a main ingredient, right, we always go to the left to look. If we make any changes, then everything to the right changes. So we can, again, start to play around with the geometry of this, plus its depth, which also determines its structural performance, right? I mean, that's the nice thing about structures, it's inherently a parametric exercise. All right, anyway, now what do we do? Someone mentioned it earlier. We have our top and bottom chords. Now we need to do webbing, right? And we do that by? Divide. Yeah, let's divide these curves, right? Now, it's not lost on me that we could do it this way, right? We could evaluate the curve as a t parameter and then give it a bunch of t parameters and get a bunch of points out, right? But there's actually an easier way of doing this. If you go to the curve division, right, you can divide the curve up. We'll divide both of these curves. In fact, I'll just do it with 2 different widgets. So I'll divide this one. I'll put this one at the top since this is the top chord, geographically anyway. And then this one I'll plug down here. This is the bottom chord. All right, now, occasionally, we start to have geometry that begins to conflict and it starts to get really dense with construction geometry, right? It's not that way I want to delete any of these widgets because we need them, but we can turn off their preview so that we don't necessarily see all their previews and see all of these sort of superfluous points sitting around everywhere. Let's see here, let's turn that one off. Yeah, all right, so now we have this bottom chord, this top chord, and then these division points. All right, we can match them up 1 to 1 to draw some vertical-ish lines, right? And then what do we need to do to these lists of points for the top chord and the list of points for the bottom chord in order to start to crisscross? Yeah, we can shift the list by 1 value, right? And I think most of you got this, but if you didn't, you also probably, some of you noticed, let's say you go to set, and go to shift. But if you look at the inputs, we could shift like not only the first value, we shift the top 2 values, or the top 3 values, right? We're only do 1. And then the question is, with that other option down at the bottom, wrapping, right? Do we wrap that top value back to the bottom, or do we just throw it out and discard it forever? And I'm going to set this to be false so that it's gone forever. All right. Now we can shift this list. You don't want to be in my shift list, that's for sure. All right. That was the lamest joke in the entire universe, I realize. All right, so this list of points with this shifted list of points, this shifted list of points with this list of points. There we go. All right. Yeah. Not a big deal, right? Now, does it make sense? I mean, I'm seeing a lot of, everybody who's submitted seems like they got this, right? So, and then you did the 3-dimensional truss, which was to to also make a third curve and then start crisscrossing them and got a lot of redundant sort of things going here, right? Okay. All right, so what I think would be helpful now is just to simply open up some that you can look at. Let's dissect them. Whenever it comes time to sort of plan these things out, or when I have an idea, I usually have my sketchbook right next to me, and I'm sketching, I'm sort of making notes. And I usually, again, it's called pseudocode if you're a programmer. But writing things out step by step in natural language helps. In other words, what do I do next? What do I do next, right? We just did that. What was the next step? The next step. We need to do this. Now, how do we get there? Given that we have these ingredients. That's the kind of thinking you need to do. And sometimes not to sketch these things out, or to simply list them out so you can sort of check them off and make sure that you're doing everything that you said you needed to do. All right, so let's start with something here that I think was fairly prominent in your the videos you watched, which was making an ordered list of numbers and then looking at data matching and particular cross-referencing in order to make a grid of points. All right, so let's talk about that and why that actually works and how it works. Let's open up column grid example. Here we go. All right. Grids are pretty useful, right? I mean, particularly if you're studying structures right now. Usually we establish things on a grid. And, you know, I've done tiling, I've done carpentry. Grids are really useful. You can see them all around us in various ways. Even our keyboards are established in grid. All right, so right, I have a column grid here, and let's talk through this step by step and see what it's actually doing. Okay. First of all, you can see, let's start from the right to left and sort of reverse engineer, and then we'll go from left to right, and we'll annotate these things, all right? First things first, I'm making a set of boxes. These are called domain boxes, right? So what does it need for its ingredients? It needs a base plane, right? In other words, it needs a point, but it needs a plane around that point to sort of understand orientation, which way is X, which way is Y, which way is Z. And then it needs the dimensions of the box off of that in X, in both the negative X and the positive X. And then the same with the negative Y and the positive Y. And the same with the negative Z and the positive Z, right? So if I give it one of these points, and I say, go negative X by half a unit, positive X by half a unit, negative Y by half a unit, positive Y by half a unit, 0 in the negative Z, and 12.668 in the positive Z, right? Then I get something that looks just like this. And then I plug in a list of those points, I get a list of columns. Not a big deal, right? Is it making sense? Yeah, all right. So, stepping back, I made a grid of points. And look, fortunately for us, sometimes when you do this, there are shortcuts already built in, right? You need a hexagonal grid, a radial grid, rectangular grid, square grid, etc., right? There's more grids than you can shake a stick out here, so I used to say. But I wanted you guys to sort of see this, right? There is a way of doing that just by simply entering in a set of X coordinates, a set of Y coordinates, and a set of Z coordinates, right? All right. And that's what I'm doing here. I'm generating a list of numbers, an ordered list of numbers, right? I'm using the series command. So, when in doubt, and I recommend you guys do this, if you go to the params tab, there's this panel, right? It's like basically a sticky note. And inside you can double click and you can write anything you want inside of it. And I found that it's really useful to comment step by step what these things are doing. So that 3 months from now, when you open this back up and go, what the hell is this? This is a big jumbled full of spaghetti, things going all over the place. Right? You can follow along, right? It's there for your help. All right, so here I'm using a series to make an ordered list of numbers. Yay. You can see, again, remember series? There's different ways to make an ordered list of numbers. It's actually surprisingly handy to actually be able to do that, right? This way you start with the starting number, then the step size for each additional number, and then the number of numbers you want, right? Okay, so in this case, I've given it this sort of X spacing to be somewhere between 18 feet and 36 feet. Yeah, not bad. If you go too much under 18 feet, then you kind of have to wonder, like, you're not going to be using beams between columns for that. And if you go too much over 36, then you start to get law of diminishing returns. That, spanning that becomes a different proposition than beams, right? Okay, so same thing here with the Y spacing, and then the number, right? They're all independent of each other in X and Y. Now, this is where having freaking whiteboard eraser. I'll write whiteboard markers next week. All right. I can't believe we don't have whiteboard. Like, let me see that up here. What's that? I'll bring some next week. All right, but let's think about this, right? If we give it a list of numbers, 0, 1, 2, 3, 4, right? And then 0, 1, 2, 3, 4. And we plug the first list in for X and the first list in for Y, what do we get? It matches up 0 to 0, right? And then it moves on to the second value and matches up with the second value in the other list, 1 to 1. And so you get a diagonal set of points. You don't get a grid. Now, if you think about a grid, I need a point that says 0, 0, right? And I need to move over along the x-axis and get another point that's 0, 1. Then another one that's 0, 2. Another one that's 0, 3. Then when I get to the next row, I need one that's 1, 0. 1, 1. 1, 2. 1, 3. Right? So if you think about this, in x I need 0, 0, 0, 0, 0, then 1, 1, 1, 1, 1, then 2, 2, 2, 2, 2. In the meantime, for y, I need 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Right? In order to make a grid. If you just look at a grid, think about its x, y coordinates. Right? The x's go 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, as many rows as you have. And the columns, y goes 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Right? Cross-reference does that for us. Thank God, because it makes my brain hurt thinking about it. And so, remembering that if you hold down your cursor over any of these inputs or outputs, it sort of gives you a preview here. But if any of these are too long for you to sort of make sense of them, you can always plug the outputs into one of these notepads again. So let's take a look. And so for the x-coordinates, going 0, 18, 36, 54, right, all the way up to 126, and then starting again 0, 18, 36, 54, 72, 90, 108, right? It's doing it 8 times. It's giving you 8 values, and then 8 values again, 8 values again, 8 values again. For the y values, we're getting 0, 0, 0, 18, 18, 18, 18, 18. You see what I mean? So it's doing it for us. So that way when you plug it in for x and y coordinates, we get a grid. Pretty ingenious, no? So what it's doing is it's saying all the values in this list are going to be cross-referenced to all of the values in the other list. And then it orders them in a list, in each respective list, x's and y's, so when you plug them in, they all match up. It's really kind of handy. All right. Then we plug them in for points, and then we plug in a box widget. All right. Some of you are really bored. Ready to do something a little more fun, maybe? I don't know. Okay. Open. Which one next? Let's go with roller coaster example. Right. So, really quickly, what I'm going to do is just simply draw some sort of 3-dimensional spline here. Let's see. Come on now. Just going to manipulate these control points in Z. Seriously. There we go. You think this wouldn't be so difficult, but sadly. Okay. So we'll make this thing sort of dip around, like a roller coaster track, right? This thing moves in 3 dimensions all at the same time, right? Not the prettiest looking thing, but you know, it is what it is. All right. What does this recipe need? What's its starting ingredient? Was it right here? Yeah, we always look to the left, right? All right. So I'm going to give it this curve that I just drew. I'm going to right click on it and say set one curve. Reference this curve in from Rhino. Now look what it's doing. Okay. Somehow we get a sort of offset of this curve. So let's take a look under the hood and see what it's actually up to here. I'm going to turn on the preview for all these things. We can sort of take a look at them step by step. And in fact, I'm going to go from the back here. I'm just going to turn off the previews so we can do this one step at a time. Okay. So the first things first, I go to the curve tools and I go to division. You can see that there's multiple ways. I can divide the curve, right? Like let's say 10 times or whatever, right? But I can also divide it and actually provide planes along the curve that are perpendicular to the curve at each individual point, right? Each division point. This is exciting. I know it's weird, right? Okay, it's good because I don't know how many of you took physics in high school. I hated vector math. Geometrically, you can solve these things without vector math. Right. So, and it'd be basically how we would construct it on paper if we were really trying to be proper here. If I do perpendicular frames, you get the same inputs, right? The curve to divide, number of divisions. No big surprise here. And in fact, here it is, right? You get the divisions, but on each division, each divide point, I get a plane. And you can see that that plane twists around with the curvature of the curve. So you can see that each plane has an x and a y axis. Its z is again along it's basically, if you think about this, you take that point and you analyze the curvature at that point, right? Remember calculus? The tangent c is basically the tangent of that curve at that point. You can draw a line, right? It's like the measurement of the slope of the curve. And with calculus, right, you can do that along a curve that's constantly changing, like a roller coaster track. Yeah. In fact, that's what half of calculus was. You didn't realize it. You were just trying to figure out how Six Flags can make the next roller coaster. Just, is it steel or wood? You know, whatever, just show me. Okay, so, and of course I can divide it in number of times. I can make that more or less. Now, if I take those planes and I begin to break them, right? In other words, I can begin to deconstruct the plane. I can break them up into x, y, and z coordinates, the directions. X and y form a plane, right? Two directions. Z is the perpendicular of that plane, the normal. And then we have the origin, the location of that plane, the center of that plane, the point, x, y, z coordinate, right? So this is an x, y, z. Of course, we have how many planes? Let's see, how many divisions did we have? 32. So we should have 33 planes. Yep. 33 planes to make 32 divisions, just like a piece of pie. And 33 origin points. And so what we can do is we can say, let's draw lines out from this curve, from each of these origins with each of these y-axes with this length. So here's the roller coaster track starting to take shape. I can make it more or less dense, more granular, and how much I'm sort of dividing this thing to make it more or less accurate. Now I can find the endpoints of each of those lines, and now I can take the endpoints and draw an interpolated curve through them in order to get the other side of the track. Very, very simple. But again, underscoring there's properties of these geometries. It's very useful to be able to suppose. And again, what I recommend doing is looking at what it gives you out of here. A plane, in this case, also a t parameter. Aha, that's pretty handy, right? So if I wanted to then need a list of t parameters along this curve, it's already generating that for me as well. For each of these points, where each of these frames are located, gives me the t parameter. Now you notice that the t-parameter goes from 0 all the way up to 329.622801, as one does, right? That's because I didn't reparameterize the curve. If I reparameterize the curve, then those would probably normalize. All those values would then be proportionally between 0 and 1. Right? So let's reparameterize it. Now suddenly the bottom is 0, the very end is 1. Right? If we wanted to do that. All right. Let's talk about this while I have this curve up here. Let's just blow this away. I like to make sound effects, sorry, just the way I am. Let's evaluate a curve at a t-parameter. Again, we have this curve. Let's take a look at it. I can't believe I thought that we'd have another meeting this week and I'd be able to give you an assignment next time we meet. Stupid. All right. Let's plug that in. Let's reparameterize. Right-click on that C input and say, whatever curve we plug in, let's reparameterize it now. Normalize it between 0 and 1. Let's give this then the good old number slider that goes from 0 to 1. Now we can place a point anywhere along here. Let's take a look at what it gives us. It gives us a point, right? We know that. It also gives us the tangent, doesn't it? And it also gives us the angle and radians of incoming outgoing curve. That's interesting. You guys remember radians? How many of you remember radians from trig or algebra 2? Probably both. Yeah, it's like a way to measure angles, but not degrees. Like by pi, like 2 pi and 4 pi. Again, it's like, right. All right, so let's see here. Let's also go to curve analyze, and let's analyze something else. Let's analyze a perpendicular frame at a t-parameter. Woohoo. Same thing, right? In fact, I'll say reparameterize. Let's plug in the same curve. Let's plug in the same address so that we get also a plane there, right? A point and a plane. And we also have the tangent. Let's take the tangent. Let's draw a line so we can double check. And if you guys, how many of you can be honest, how many of you know what I mean by when I say tangent? All right, so let's draw it on the screen so you can see. Make sense? For those of you who didn't raise your hand, it's fine. All right, let's go to curve, line. We'll go, this is the start point, and the tangent will be the direction. And then we'll give it a length. Let's see, let's just give it, the easiest way to just give something a length, just one length, is just to write in one of these boxes and plug it in. Length of 10. There we go. Now, you guys understand what perpendicular is, right? I have a line, something that's perpendicular to it is at 90 degrees. Now, if I have a line, perpendicular piece of paper is 90 degrees in both the x and the y, right? Now, if I have a curve and not a line, then I have to sort of take the curvature at any point along that curve, find the tangent, and then the perpendicular, the normal, is normal to that, right? So the perpendicular plane would then move along with tangent. Like so. All right, so let me just highlight this in green. Let's make this larger. Let's make it 20. No? Yeah? Okay, let's do 20. All right. Let's highlight these two things, the frame, the plane, and the normal. So they're green. And let's move this. All right. Is that starting to make a little more sense? So that line is the tangent, right? As the curvature changes, the slope changes, and that tangent is measurement of slope. It also happens to be the normal through the plane that's perpendicular to the curve at that point. Fancy way of saying if you stick a pencil through a piece of paper and you line everything up 90 degrees, and you move the pencil, the paper's going to move with it, right? Yeah. Okay. We could do all kinds of weird things and make this thing look like it's growing fur or something, but let's not. Let's close this. How are we doing on time? Oh, we're doing perfect on time. We'll get out of here early today. Again, you can clap and, no, I'm just, sorry. All right. One other thing. So, let's see. Do I have? Let's see. I'll just open up this one, I think. I think I should have a curve in here that I can use. If not, no big deal. Oh yeah, okay, here we go. I'll just turn off Grasshopper for a minute. So I just drew a curve in Rhino. It's flat, it's on the XY plane. Just happens to be a spline, right? It's like a path, a weird path. All right. Once again, I'm just going to turn the grid off. All right. Now, step by step, let's take a look at what we have. First, instead of making a bunch of random x and y coordinates, a list of random numbers, and plugging those in to generate a list of random point cloud, there's actually a widget that just lets me populate a region with a list of random points. And then over here, there's a widget that says, take a point and find and compare it to a set of points and find the closest point to that original point. So here we can find the closest point in a point collection to any sort of given point that we give it. So what I've done is I've brought this curve into Grasshopper. I've made a set of points in Grasshopper. I've placed a point along this curve in Grasshopper, right? It's right here, this green one. You can see that it has a t address, so I can move it along the curve, right? And then I've said, okay, take this point, and let's compare it to all of these points in the point cloud. And let's find, in this point cloud, let's find the 8 closest points to this point along the curve. And so it's done that, right? You can see I've drawn lines between the set of 8 closest points and then this curve, right? As you can see, we have 8 legs. And of course, that changes as I start to move the point around, right? So you can see, again, demonstrating the data moves from left to right. Everything sort of changes and it propagates from left to right. So we make changes over here on the left with this slider, right? Everything else changes, right? And again, that's something to hopefully helpful to remember, right? I mean, I could make it the 10 closest or the 4 closest or whatever, right? But again, it's this idea that this thing is editable. I can go back and I can start to adjust parameters. I don't have to redraw this whole thing, right? Visually or analog manually, right? But anyway, something else to look at if you want to understand. But again, all this is a list of points. And then what this does is it takes this large list of points and breaks it down into the 8 closest points. The 8 closest points closest to this point. And then what I do is I take these 8 points and this point and draw a line. I guess I changed it to 5, but I could change it to 8. There you go. All right. Singing Itsy Bitsy Spider while you do this is optional, of course. All right, let's close this. No, don't save. Surface roller coasters. Here's a fun one. I did this just this morning. Another one I just did this morning. Let's see here. Just gonna start a new small objects, inches, sure. All right. Let me turn this grid off one more time. Now, next week, we're going to apply these to a surface, and then we'll start messing with sub-Ds, and then we'll generate some sort of interesting sub-D vortex-looking sort of atrium structure. Then which is what Rhino's really good at. Then we'll bring that into Revit, and we'll move on to Project 2, where we'll then start to build walls and floors and roof around it, which is what Revit's really good at, right? Okay. But today, let's take a look. We're just going to, what is this again? Oh, yes, a point. Let's see. I'm just going to draw a line here in, turn my ortho on. Here we go. Draw a line in Rhino here. I'll just move it over here where it's closer. All right. Now I'm going to set one curve. And now what I've done is I've made something that can actually scissor. And at the same time, what's nice about this is that the lengths of these don't change. So it actually simulates, you know, like if you actually made a hinge connection here. Now, easier said than done. I could do this, again, with vector math, and what a pain in the rear that would be. But what I did is instead I solved it geometrically, which is to say that all this is removing two circles along this line and finding their intersections and drawing radius from the center of each circle to their intersections. The radius in the circle size doesn't change, therefore the radius doesn't change. Very elegant geometric solution to kind of a vexing problem when if you ever do like paper folding, you try to simulate it three-dimensionally, it's a pain in the ass. I'll just be blunt. It's a royal pain in the rump. Well, this begins to suggest a way to do it, where you're not sort of, you know, fabricating paper out of nothing, right? The paper doesn't stretch, right, or shrink, and so this is a way to simply do that, right? And it's very simple. So what I do is I just give it a line. I draw the line in Rhino. Step by step, let's take a look. Let's unpreview these things. Again, I can right-click on each of these widgets and unpreview them, or I can just go up here and then say Solution, Preview Selected Off, and turn them all off at once. Okay, now we'll turn them on iteratively, one by one. Let's find, what am I doing here? I'm finding a point along this curve using a t address, t parameter, right? Evaluating the curve at a t parameter gives me a point at that location, at that address, right? And I've set it so that this slider that governs the t parameter goes from 0 to 0.5, so halfway, just under halfway, 0.49999. Now, what am I doing with this one? Something a little different. Who wants to tell me what I'm doing with this one? I'm taking the t value from the left, right? And I'm subtracting it from 1, meaning that I'll actually make this thing move from the opposite direction in alternating direction, right? Does that make sense? Yeah. Right, simple arithmetic. Hopefully it makes sense, please. Right, and then suddenly I can draw circles that are the exact halfway. I measure the length of the line, right, that I drew. I multiply it by 0.5 to find half of its length. And I plug that in as a radius for this circle and plug it in for radius with this circle. Each of these 2 points become centers for circles, the radius being governed by half of the line. And then I find the intersections between these circles. In this case, it's always going to be 2 points. And I draw lines from the center point to each intersection. Right? So there's a lot of construction geometry doing the heavy lifting here. I turn those off, and suddenly I just get scissors. Right? I don't think they let you make dog gates for these anymore because it pinches people's fingers off. People frown on like kids getting their fingers decapitated from gates, right? Anyway, but back when I grew up, we had gates like this, kind of like an accordion. All right, anyway, thank goodness we progress. All right, let's see. One last one. This is what I'd like for you guys to take a look at this weekend. A little more than what we've been doing. But it's what we're going to use to then start to populate the surface with lots of trusses, all of those. This is like finally, like the why we made a truss in Grasshopper to begin with. All right, so let's see, desktop, home, where did it go? Desktop, here we go. 367, here we are. Yeah, right back where we were. This is in Grasshopper. Let's make a reactive surface using an attractor point. Yeah, that sounds good. And let me open up this Rhino file that already has the curve in it. All right. Well. So, I don't think any of these widgets, save for maybe this one, are brand new to us, right? What am I doing? I'm making an ordered list of numbers using the series widget. I'm doing that twice, right? I cross-reference them in order to generate a grid of X and Y coordinates for points. I plug them in the point widget. I get a grid of points. You can see them. They're all right here along the XY plane. Then what do? I project down with the start point direction length, just like we did with the truss. Right? Except in this case, I'm doing it from each point in the grid. Now, what's different is the length of each of these lines that we're drawing down from that grid of points is governed by something else. Let's take a look. So, if I also then draw this curve, oh wait, let me turn off the grid here so you can see a little easier. Yeah, here we go. So I have that curve, and I've basically placed a point along it with the t parameter that I can move, right? And then I measure the distance from that attractor point, and that's what we usually call these things, is the attractor point. Right? It starts to govern the properties of some other piece of geometry and its relationship to it, right? So it's basically usually based off of distance, right? So how much it tracks from this distance. So we measure the distance between this point to all the points in the grid, and we use those as the length for each line to project down from. And then we take each of the endpoints of those new lines, and we form a surface from it. So let's turn off the preview and let's take a look at it step by step, and you can see how it works and what it actually does, right? Not a big deal. We've already seen this, right? And this is what's helpful. Once you have some of these pre-built, you can start to click and copy and paste them in and start to build off of them. And you don't have to keep dragging the same widgets around all the time. We basically made a grid of points, and it's a count of 10, and spacing is about the same, And so we have this grid. Same time, we have this curve, and I've made this point move around it. Now, let's draw these lines in the negative z direction. I put a -1 there so that we're drawing lines downwards. Now, each of the lengths of these lines is governed by its start point's distance from the attractor point, right? And so as I move this attractor point around, those relationships change. And of course, we then use the endpoints to make a surface from a grid of points. And so now the surface is also responsive, it can change in accordance with the attractor point, right? Just think what Antonio Gaudi would have done with this, right? With these catenary vaults and things like that. Holy moly. He would have been like in heaven. Right. Now, that's the first step. But step by step, that's what we're doing here, right? We're just simply creating a surface now from all of these points. Now we're making them a little smarter. If, let's say, the attractor point was related to position of the sun, or let's say some other sort of force that we sort of are really trying to react to, let's say, in the urban environment or its context, right? Lots of different ways you can use attractor points here. To make things smaller, aperture-wise, or larger, to form the geometry or literally the form of this thing in this case. Anyway, let's say we're making a canopy. We have all of this. Let's open up the next one. All right. So we get to the left, and looks largely the same, right? I mean, if you don't believe me, look, we can move that surface around. In fact, here's the surface. But then we get here and we look at this. We start to find curves along the surface. As soon as we have curves along the surface, we have the initial ingredient for trusses. We just made trusses from a curve. Now we have a list of curves. Now we can make a list of trusses. Right? And so we do. This looks largely the same, right? We find the t parameter along, a point along each of these curves. We project upwards. We find the endpoints. We draw interpolated curves for the different, the other chord. Then we start to divide things up and add the cross webbing. Boo. Let me just turn this off, and let me just change the. Let's see here. There's so many parameters, right? I can change this in any number of steps. Right, so that's the actual surface geometry. And then we have how many we need, right, and their spacing along the surface. And then we have the depth of these, right? Do we want them symmetrical or asymmetrical about one side or the other? And then I didn't put this in here, but we could also make the number of divisions, right? The number of segments, numbers like that, right? Okay. This is where, like, the rubber hits the road, so to say, right? This makes it worth it. Because now we have suddenly a surface, an envelope, a piece of glass, right? Whatever it is that we can change the shape of. It's gonna keep evolving as we evolve our design decisions. So now we can just populate the darn thing with the structure behind it, hold it up, right? Easily fit that out with spider clips and sort of clamp glass to it, or whatever we want to do. Or put some purlins in the opposite direction, start to put roofing down, whatever. Make sense? I mean, maybe it doesn't. Take a look. Now, what it does is it takes that first recipe that we just looked at, right? How to make grid points and then make a reactive surface along those grid points. And then it combines the other recipe you did. How to take, once we get the curves from that surface, we can plug in a list of curves and make trusses all day long. Now, there is one key difference here. And that is, you'll notice at a certain point in time, the rubber bands become dashed. What that means, not to confuse you too much, but we'll deal with this throughout the semester, is that at a certain point the data actually gets organized in a different way. Rather than just a simple list where you just have item 1, item 2, item 3, item 4, you basically have what's called a data tree, and so you have trees with branches or a list of lists. Where this comes in handy is if you think about this, just for one moment, right? When we're given it one top curve, and we said divide it up 10 times and we get 11 points, right? And we just get a list of 11 points. And then we divide the bottom, we get a list of 11 points along the bottom. We can just match those up one to one really easily. What happens when we give a list of top curves? We don't want just like 300 points, randomly organized, right? What we want is a list of the curves from the first curve. Sorry, a list of the points from the first curve. And then the second list, a list of the points from the second curve. And the third list, a list of the points. So those become branches within a larger tree. Right? And if you can match those up with the ones from the bottom, and they're matched up with the same data tree, then you can start to do much more sophisticated things, right? So I'm not going to pretend that this isn't sort of an exercise in an intellectual exercise in sort of imagining something very abstractly, right? But when we come to this, and particularly when we're starting to do with surfaces, right? There's some metaphors that I think are really useful. That go beyond just simply trees and branches, to help you sort of visualize this in your head. So I think that's what the hard part is. Will it click in your head? Do you have a picture of it in your head, what it's actually doing? So this is our first foray into data trees. Take a look at this. Break it if you want. Whatever you want to do. But at a certain point, we can give it this surface or any surface we want. Any surface we make in Rhino, we can plug it in to this and suddenly start to populate it with lots of trusses in one direction or the other. Pretty exciting, if you're me. I don't get out much. This is really exciting. Don't judge me. All right, well, anyway. Yeah. Take a look at this, right? First thing on Monday, we'll go ahead and populate some things with it and show you how it works. But then we'll start to make our own vortex out of sub-D geometry. How many of you have played around with sub-D geometry? In Rhino or elsewhere? Blender, T-splines, Maya, Studio Tools. Oh, shit. Did you guys just grow up like using iPads and you don't know how like file structures work and things like that? Oh, God. All right, that's all right. Well, you're on the same boat. We'll get through it. Okay? But suffice to say, right, there's more than one way to make nice, sophisticated, two doubly curved three-dimensional geometries, right? That's the superpower. Right? So we'll talk about sub-Ds next week. I'll have again a recipe for you. Now the recipe's up for you to sort of make some of the variable decisions about, but you all have to be using the same recipe. You'll follow along with me, I'll record things, so you can do it as well. And what we're gonna do is we're going to make the sort of branching surface with subdies, we'll populate that with space grid. You know, basically a three-dimensional truss system. And we'll bring that into Revit. All right, Revit doesn't like doing that. Doesn't like splitting up, branching objects. Doesn't like subdies. It doesn't do double curvature very well. It can do it, not work. Right? So combining superpowers from these platforms is nice. Right? And we'll bring it into Revit and we'll start to build some more architecture around it. In it, under it, over it. Are there any questions? I know I throw a lot at you, but again, I do try my best to record things, let you replay things. I don't necessarily have things in advance for you guys, because I'm so busy. I don't know if you guys noticed, I'm also grad coordinator for 3 more months. It's like a full-time job, I don't get paid anything extra to do. And I'm, like, right now, my creative career is moving on, so sorry, I just, like, don't have excess time. But the key thing here is that if you need extra time, you can take it. Communicate. That's all. Send me the email. Come to me after class. Come find me in my office or set up a meeting with me, whatever you need. I'm there to help you. It's my job. Some of the other stuff I can put on the back burner. I'll do my job. Take advantage of it. Some of you will. Some of you won't. Some of you will regret not doing it. It's just the way it is. Every semester is the same. But at the same time, like again, if you need anything from me, just let me know. Communication's key. You have a little bit of grace period to turn something in if you did today. And if you still need a little more of a grace period, again, just communicate with me. Again, these things happen. We're just past the first week of classes, so Rhino didn't work, or I had to update my .NET framework on Windows and something won't drive. Whatever it is, right? I understand sometimes what happens. Have a great weekend. I won't see you until Monday, but on Monday we're gonna work our rears off. Yeah. No, next week we'll be doing more Rhino. Eventually we'll be bringing double free to Revit. The week after and the week after. I can't hear you. Everybody, quiet down for a second. What was the question?
For Revit, would it be nice to email and get that?
Yes. Revit is free for 12 months on a rolling basis as long as you have it back in the address. It only runs on Windows. Not on the Mac OS, unfortunately, or on Linux. Anybody likes Linux?
Revit only runs on Windows.
Only runs on Windows.
And we're gonna use Revit?
We are going to use Revit. You can always use Computers Computer Lab on your own time. But I do recommend, if you have a Mac, getting parallels with Windows to be able to run Revit. So it's going to be both. Rhino Revit, you go for a cloud, these are like the basics. These aren't even like this. Special. Compare with the let's see, the last time I did sorry, my brain is like an operating system. It's trying to do too many things.
It's okay.
The last time I did the laptop specs, let me just take a look. I used basically the minimum and the, let's see. Damn, 2-factor authentication just to log in. Come on, let's go. Half my day is waiting around for computers to do my work for me. Starred list. Forgot I had coffee. Oh, I'm still